Hi and welcome back to Tetryonics. In this brief recording I'll cover the basic geometrics of equilateral versus omega geometries. Of course, equilateral geometries by this stage you'll realize represent squared energy levels or scalar energies themselves, and the omega is part of Planck's constant mass-omega, which equals h in the case of mathematics. We'll go on to cover the basic pi-radian geometries as they relate to these equilateral geometries and where they apply to building up the physics of nature and the material universe that we observe at present. In physics, not all equilateral geometries were created equal. That is to say that up until now, squared numbers have often been taken to represent circular geometries or fields of force from charges, fields of interaction, and spherical particles where charge is distributed across the spherical particles themselves as point particles, electrons, protons, etc. Tetryonics deviates from that understanding and that interpretation in that it's based obviously on the omega of Planck's constant, with Planck's constant being mass-omega, with units of mass or kilograms, square meters per second. The square meters per second in Tetryonics represents an equilateral triangle made up of three 60-degree corners summing up to 180 degrees. Squares, on the other hand, are still equilateral geometries, but their angles are 90, and hexagons accordingly are still equilaterals, but they have angles of 120 degrees. In developing Tetryonics, to cut a long story short, the priori postulate was that the squared meters per second, the Planck's constant, actually reflected an equilateral triangle, and that energy was what this geometry was, and that Planck's constant was just describing a particular physical property of how to divide that triangle up. So what is termed squared in our vocabulary and in physics is in fact not a squared number at all. It's an equilateral number, or even more appropriately, given what I've just said, it's a triangular number, because energy itself is triangular and it's made up of smaller equilateral triangles of Planck quanta. Now these triangles can be, the scalar energy itself can be divided or measured in a number of ways. The energy itself is mv squared, so it's an equilateral triangle of energy. We can measure its square root as its linear momentum, or its amplitude. We can measure transversely across the same scalar wave and measure quantum levels, bosons, plus and minus W bosons of transverse mass energies. Or we can measure longitudinally in line with the linear momentum and the direction of forces that this energy can create, and measure photons of mass energy momentum. The difference between the transverse and the longitudinal measurements are that normally the measurements are done so that in the case of bosons, h nu, there are two of each to make up a photon, hf. You can still measure the distribution of energy longitudinally in terms of bosons instead of photons, in which case the only difference is a scaling of 2. There will be 2 bosons for every photon, and that's how this is color coded. This illustration has one photon at the point illustrated, one boson at the point illustrated, then 2 bosons that make up a photon, highlighted in orange, either side of the the amplitude of the wave, or the linear momentum. These are numbered across the bottom to form an even distribution, or a normal distribution, of energy momenta within the scalar wave, or the scalar field of the energy. And again, this scalar field is made up entirely of positive and negative Planck quanta, or triangles, equilateral triangles of energy momenta. They're normally formulated as E equals nh nu in the terms of Planck's relationship of energy and its quantization. But that formula can apply in either direction, as I've just discussed. It can relate to the longitudinal or the transverse measurement of quanta, or energy momenta, within that scalar field. And accordingly, it doesn't give us a good idea of the exact relationship between quantized energy and energy itself, or between bosons and photons. For example, if for energy level 3 we have 3 quanta that make up the boson for that energy level, that can be expressed as 3 h nu, which is, or 3 times 1 h nu, or it could be expressed via its energy level as 3 1 squared Planck quanta. 1 squared, 1 squared, 1 squared. Either way, the formulation still works out the same, but it shows us that there's a direct relationship in the case of energy at the quantum level between nh nu and h nu squared. That is to say, while it's generally correct to say that there's nh nu quanta in any scalar field, it is probably more correct to say that there's nh nu squared quanta within any energy field, because every energy field must contain nu quanta. This also lines up tidily with classical mechanics, where the energy of a field, or an object, can be equated to its mass times the square of its velocity. This relationship's been known for quite some time, as has the relationship between mass and velocity for linear momentum, the square root of energy. But there's been no understanding as to what brings about these constants of proportionality, or the formulation as it exists. They are just the result of observations. Tetryonics gives us a bit of deeper insight into the fact that obviously mass, velocity, or linear momentum, and scalar energy, mv squared, are geometrically related. It's often stated that they are in physics texts, but never is that statement accompanied with an illustration such as what you see here that explains the relationship geometrically. You can now see how equilateral scalar fields of energy can be quantized to form not only the scalar electromagnetic energies, but their associated square root linear momentum that provides a force in a particular direction. And when we add electric and magnetic fields, things become even clearer within this geometric idea. So what I guess I'm saying here is that Tetryonic geometry redefines Planck's generalized quantum formulation. It gives us it takes it from a specific generalized equation for 2D energy or mass energy momenta into a specific geometric representation for scalar energies and mass, particularly within matter, because it's these equilateral energies along with charge that they create that forms matter itself. So the need to correctly formulate energy, and particularly quantized energy, in a way that we can differentiate between bosons and photons with respect to scalar energy at a glance, and even mass itself, which is a measure of energy per light second, as we discussed, from matter, is obviously a key topic of discussion and worthy of further investigation in order to try and develop a clearer picture of how nature builds up our universe and its physical properties from the smallest quanta possible. And bear in mind that this quanta is already hinted at within Planck's formulation, within his work on spectral lines. It's now it's obviously the foundation of quantum theory, and its properties and the fact that energy is quantized at the subatomic quantum level is now beyond dispute. Physics has many formulas for energy and mass and matter in motion and its interactions within the fields of science itself, some of which are included on the side of this page, on the left-hand side. Tetryonics takes those mathematical equations and gives them a geometry, a physical geometric reality. It does this by simply relating pi radians to an equilateral triangle. An equilateral triangle is nothing more than a truncated pi radian. Pi radian, of course, is created when you take the radius of a circle, map it out over the circumference, and create an angle. So if we call Planck's equilateral geometry, or its omega, the quantized angular momentum, square meters per second, and if we equate that to a pi geometry, or a pi radian geometry, we can then start to build up or slice up scalar energy into pi geometries. In Tetryonics, the word geometry normally applies to a flat sheet of paper, a planar geometry, a sheet of mass energy. Where I refer to matter, I normally try to talk in terms of topologies. Even now, I still sometimes catch myself using one word when I should be using the other. But we try and do it for reasons that will become obvious in later discussions and as we start to map and model the physical particle shapes, i.e. their geometries. Obviously, no matter how we chop up an equilateral triangle, it has to be done in a way that it's divided up into portions that can be reassembled or unified back into the larger. So in the case of scalar energies, we can obviously call the main geometry a pi radian geometry, and we can chop it in half, in which case we would have a half pi, or smaller and smaller quanta. Or we could do the opposite. We could take one quanta and add 3 to it to give us 4, which then could be termed a single pi geometry. Or it could remain a 4 pi geometry with respect to sizing or its size in relation to other geometries. Something I'll cover in later lectures is the precise relationship between mass and energy with respect to its geometry. Suffice to say at this stage that energy has no time component constraining it. There is no coordinate set within which it has to be. So therefore, it can expand out. You literally just add more and more equilateral triangles to the page to get a bigger and bigger triangle as you add more and more quanta to the energy field. Not so with mass. Because mass is in a spatial coordinate system already, c squared, bearing in mind that m equals E divided by c squared, obviously the c squared forms a boundary in which you're adding energy. So in the case of measurements of mass, if you were to increase the energy, you're obviously adding more energy quanta to that field. But instead of growing larger, the equilateral main scalar field is constrained by the c squared circular spatial coordinate system. In that case, as you add more quanta, the quanta themselves must grow smaller. That is, they are contracted. Their wavelength or their dimensions, physical dimensions, become smaller as they are compressed into the same larger scalar field. So that's the main difference. You'll see that when I draw mass, I draw a circle around the energy. That indicates that it's measured by a light second, or within a light second, and therefore it's really a measurement of mass. In which case, that triangle will never get any bigger, no matter how many quanta of energy you place into it. But what will happen is the mass still increases, but the wavelength of the quanta themselves and the number of quanta increases. This is in line with relativity theory, and this is where relativity theory applies, specifically within mass-energy geometries, not within matter topologies. I'll cover this shortly. So the squared number, the h nu squared, of energies within any scalar equilateral field, which is just omega, or pi, probably more appropriately, it would have been more appropriate to put pi, a large pi here. A single energy field can have any number of quanta, providing they sum up to a squared number in line with the equilateral geometry. If they don't, it won't form a complete energy field, and there'll be bosons and or photons left over. So again, just illustrating that, we can call, instead of omega, which represents the actual equilateral geometry, we can represent the scalar as pi. Whether you can call it radians or degrees probably makes no real difference at this stage. There's probably a mathematical reason for doing it, but I'm not aware of it, and at this stage it works just fine to say that the equilateral scalar, or the surface area geometry, can be called a pi geometry, in line with pi radians. 2 pi geometries make photons. We have a single boson, 1 pi, with another single boson, 1 pi, giving us a 2 pi geometry. And to measure the mass of that energy field, we simply put it in a circular coordinate system, and that gives us a measure of energy per light second, or mass. In this case, it's the mass of a photon, 2 pi. EM waves, like the one below, would be 2n pi. They're even numbered because they're always constructed of photons. In this case, there's 4 photons, but 8 bosons, making this up. A circle, accordingly, as I've mentioned, can be made up of 6 equilateral triangles, or 6 quanta of energy, and then it's just a hexagon is just a truncated circle. And of course, as I've touched on many times before, sequential odd numbered quanta can sum together, or they can form W bosons. Firstly, charged quanta, because odd number plus and minus charges will always end up in either a positive or a negative number, never a neutral sum, never a balance or a neutral charge. So they're always charged, but we can sum these together to form a squared number. 1 plus 3 plus 5 equals 9, which is 3 squared. 3 energy levels combined to make a scalar energy field. So in general terms, we can use this pi radian geometry, or mass energy geometry, to start to define or redefine the mathematics of physics. Typically in physics, where you see pi, you think of pi radians, a semicircle. In Tetryonics, we think of pi radians, or a equilateral quantum of charge, h nu, or a half hf, as indicated in this illustration. 2 pi radians, typically seen or imagined as a circle, in physics or in nature is actually 2 bosons, positive and negative, or they may be same charges. That's the 3 combinations that are possible. In any case, it creates a photon, hf, or 2 h nu. 3 again results in an imbalance of charges and creates a W boson, whereas groupings of 4 can either create planar mass-energy geometries or be rearranged in such a way as to form a closed geometry or a material topology. And if that is created, i.e. the three-dimensional perspective is created, x, y, and z, a three-dimensional tetrahedron of mass energies, what we then create is a tetryon, which is the Tetryonics term for a quantum of matter. It's a tetrahedral arrangement of mass energies. It's the 3D form that can be created when you fold up planar mass energies. This was all covered in Tetryonics 101. So the basic cardinal angles that result due to equilateral geometries. That is to say that we have 60, 120 and 180 degrees typically, but we can have any multiple of 60 degrees as a result of the tessellation or the layering, addition, tiling of equilateral energies, either within mass geometries or within matter itself. Again, the circle represents the fact that these are mass measurements. If the circle wasn't there, they would be energy, pure energy, and as these triangles got together or came together, they would form larger and larger triangular fields. But because they're constrained by this circle, the number of quanta must shrink evenly across all the quanta as more energy is added. So therefore it's a measurement of mass. Accordingly, you'll often see in Tetryonics, because of the limitation of 2D illustrations and the 3D nature of matter, I had to represent tetryons in a particular way so as that they could be shown and easily recognized. What I chose to do was what's shown in dark green here, and that is a triangle divided up so that you have basically a top-down view of a tetrahedron. Where you see that, you can assume it's matter. It may vary. might be blue, it might be red or black if I'm looking to identify charged tetryons, for example, or neutral ones that make up neutrinos. But as a generalized form, a dark green drawing of the triangle with the bisector lines there is the top-down view of a tetryon. Again, each charged fascia that make up that tetryon, or that 3D shape, are made up of smaller quanta that all sum up to a squared number. Where in Tetryonics I draw particles, I tend to put the number of charges at the top left of the illustration, represented by a Q, and it normally has the number of positive and negative charges just below it in brackets. You simply take the negatives away from the positives and you end up with the net elementary charge of the particle by 12 in the case of most elementaries. For example, an electron will have 0 positives and 12 negative charged fascia, giving it a net charge of negative 12, which is equal to elementary charge of negative 1. That then gives us an idea that charge, apart from being just a property that allows particles to attract, is also a property, a physical property, that describes, it's the result of the actual topology of the particle itself. Where certain charges are present, it reflects a certain material topology or charge geometry of the particle. All leptons have the same topology. Their charges vary, but the particles themselves are all identical, and that includes neutrinos as well as electrons. That is to say that Neutrinos, positrons and electrons have exactly the same charge matter topology. They differ only in the energy content of those charged fascia in the topology, so therefore they're either lighter or heavier. I'll discuss that later on. But the particles themselves, the charge of the particles themselves, now gives us a hint as to what that particle is or what shape it is, without even having to do the complex math behind it, behind measuring or even doing observations of it. We can simply predict from the charge arrangements what sort of particle we're dealing with. Accordingly, the energy content of the charged fascia within those particles will give us a measurement of the mass of those particles. And this is where it starts to get tricky, because mass and matter must be differentiated. Matter is just the shape of the particle itself, the 3D shape. Mass is a measure of the energy within that 3D shape. And again, there is no energy inside the tetryons. The tetryons have all their energy, all their mass, contained within the charged fascia that make them up. So where you have a tetrahedral form, in the simplest form of matter, there all the mass energy is contained in the 4 charged sides, and there is nothing in between them. The tetryon, or the 4 pi geometries of the tetryon, enclose a region of space. They create a closed topology, a closed volume, that excludes all mass energies from within it. Any mass energy that was in it upon creation would try to radiate, would hit the sides of it, and would be absorbed and then either re-emitted or add to the energies of the particle itself. But within the tetryons of every particle, there is nothing. There's not even vacuum energies or anything like that. It is pure empty space, and that's important in later discussions, because that's what brings about gravity, and why gravity is so much weaker than electromagnetic fields, etc., but obeys the same basic formulation. On the right hand side of each illustration, I also have a measurement of the 2D mass energies, normally of the chem fields, the energies of motion, etc. And then when we add the chem field mass energies, the planar immaterial mass energies, to the material mass energies of the matter topologies, or of the particle, we end up with a total energy, which is this number up here, normally expressed as RE, or relativistic energies, which is standing wave matter plus the kinetic energies of motion. Now those kinetic energies include kinetic energy itself plus magnetic moments. But again, because energy is equilateral, there must always be an mv squared. So the kinetic energy is, if that's half mv squared, the magnetic moment must be another half mv squared, purely because of the geometric constraints. Energy is equilateral and can only form equilateral energy fields. So when we apply this to material topologies, or mass and matter, let's have a look at what we get. Firstly, we obviously, as we've discussed previously, have our spatial coordinate systems. We have c for measuring forces, c squared for xy coordinate systems, or measuring planar mass energies. We can have c cubed for Cartesian, or mapping out Cartesian 3D space, x, y, and z. But for most parts where we measure matter, obviously we're dealing with platonic solids and quaternion or transverse longitudinal waveforms. So we need to have a coordinate system that accommodates both matter and mass energies in any direction, in which case c to the 4th, or light second squared, is more appropriate. So in the case of energy, two-dimensional energy per light second, or E divided by c squared, we have measurements of electromagnetic mass. Obviously the energy itself is equilateral, so the electric and magnetic components, which are equal to each other, even though one is an electric field and the other one is a dipole magnetic field. They are equal to each other, so they therefore must have an equal sharing of the scalar energies, in which case they do in this case, because we can now see that the electric field is a 2 pi diamond shape, whereas the magnetic dipole has two 1 pi magnetic fields, which can be either north or south or north. And it's the arrangement of the north-south, south-north alignment that determines whether this energy is positive or negative. Tetryonics you'll often see the circular drawing of the quantized angular momentum, or the inductive loop. Both the inductive loop and in the inertial mass, etc., and charge, spin, curl, flux, all these sort of terms are just different terms trying to explain the equilateral geometry that exists within any scalar mass-energy field or mass-energy momenta field. There's actually no spin, curl, or flux. There's no charge flux. There's no motion of energies to create the magnetic field. The electric and magnetic arrangements are inherent in the quantum coin. And depending on which side of that quantum coin you see, determines what charge value you measure. Obviously, Cartesian space is just 3D space, and matter is made up of 4n pi, or a number of 4 pi charged mass energies, forming a tetrahedral arrangement. So where you have a tetrahedral arrangement in Tetryonics, we're talking 3D, because equilateral energy only has an XY component, whereas a tetrahedron has an XY and Z component. Now these tetrons, these chunks of matter, the quantum of matter, can now combine via the charges on each of their faces. There's 4 charges, and there's 3/4 possible tetrons. There's a positive tetron with 4 positive charges, a negative tetron with 4 negative charge fascia, and then there's 2 neutrals. Now the neutrals result in 2 positives and 2 negatives in differing arrangements, but they always result in a neutral net charge, so they're indistinguishable from each other geometrically or topologically and charge-wise. But those charge arrangements become crucial in how they bind together and the role they form. You will find that the neutral charge tetrons equate very nicely, save the fact that they're material topologies, to gluons. Gluons are often seen as exhibiting certain properties, but they're seen as massless fields. Again, a complete misnomer. Tetryonics shows us that a gluon, or a neutral tetron, is in fact a tetrahedral matter particle, or quantum, with 2 positive and 2 negative sides. Those positive and equal amounts of positive and negative sides allow positive and negative charge particles to come together and bind, sticking together. In doing so, we can actually bring 2 positive or 2 like charges together. In this case, we've got an up quark illustrated. The 2 positive charges, which would normally repel, are actually bound together by the neutral tetryon, or the gluon, hence the name gluon. It's gluing them together. Electrical people may call this a neutral dielectric that separates the 2 positive charges. But in any case, the positive charges that would normally be held apart are drawn together. Same thing applies for negative charges. They would in turn be held together by the positive arrangements of the neutral tetryon. This has got 12 charge fascias. Quarks are part of the dodecahedral family, as are leptons. The difference between the quarks and the leptons is that in quarks, the neutral tetration brings them together in this charge topology. It's a unique one. Again, you can see that they're tetryons by the shape of that actual geometry I've drawn there in the 2D space, indicating 3Ds. While the quarks are drawn together in this shape, the leptons aren't. In the case of the electron, all three tetryons have negative charges. There is no neutral gluon to bring them together. So instead of attracting, the negative charges actually repel, creating a distinctly different matter topology and a different net charge. Again, remembering that 12 is the multiplier for quantum versus elementary charges. So a negative 12 charge is the same as a negative 1 elementary charge in normal physics or standard physics these days. The partial 1/3 and 2/3 charges of quarks would then obviously be 1/3 and 2/3 of 12, which is 8 and 4. And that's precisely what we see in the quark arrangements when neutral tetryons come together as a dielectric between charged particles. They form this 1/3, 2/3 elementary charge, or 4 and 8 quantum charge topologies, whereas the electrons, with their faces held apart by a repulsion rather than an attraction, form or have this plus or minus 12 or even a neutral charge. In the case of 3 neutral tetryons, we still have plus and minus charges, so you can form a neutral particle or neutral lepton made up of 3 gluons or 3 neutral tetryons, and those neutral particles are in fact neutrinos. They have exactly the same matter topology as an electron or a positron. They have a different charge than neutral versus plus or minus 12 or plus or minus 1 elementary, and they have different mass energies. Neutrinos have less mass energy in their charged fascia than electrons or positrons, making them lighter. But they have exactly the same matter topology. They're the same size, just less mass energy in them, in their charged fascia, thus making them lighter. None of these are spheres, as you'll note. Even more so in the case of baryons. These are icosahedral shapes, that is, they have 20 charged fascias that we can measure or see once they're formed. They're made up of 9 tetryons, so they have 36 charged fascia, as you can see from the number there. There's 36 mass-energy geometries, making up a particle whose topology only allows us to see 20 of them. Why is there only 20? Because again, positive and negatives attract, and they come together to form a partition, an invisible hidden partition inside the external matter topology. So even though there are 20 charged fascia in baryons, hence why they're called icosahedral, there are in fact 16 hidden fascia that have joined together to hold these particles together. And of course, those 9 tetryons have actually formed 3 quarks, 3 per quark, in order to form the baryons in the first place. When you go through Tetryonics, as we'll do in later lectures, we will see the genesis of all the particles, how each one is formed with its charges and its particular shapes. But suffice to say, at this stage, we've now differentiated between 2D planar or Euclidean mass-energy geometries and 3D matter topologies, or material objects, material particles, using nothing more than a charged equilateral geometry, which is the the result of energy itself and the arrangement of electric and magnetic fields in that energy. So that the basic physical dimensions can be, or particles and fields can be divided into two classes. We can say that there are mass-energy geometries, which are planar fields of energy, momenta, mass, energy, if you're measuring it in a coordinate system, which have x, y coordinate systems and no z. They're normally radiant mass energies, that is to say, once they're created, they spread out at the speed of light from their sources. And then there's the matter, or the standing wave matter topologies, which is where charges or charged energy comes together to form a 3D shape or a topology. And the radiant mass energies within that shape try to propagate, but in doing so they end up hitting each other in particular ways so as to form a circulating form of energy. The energy still, or the mass energy, still propagates at the speed of light. But what it's doing is propagating around and around in this fixed matter topology. And that's what gives matter its substance, its form, its strength. It's this equilateral mass energy forming a tetrahedral topology. Now, you ask any architecture or any engineering student, even a carpenter, what's the strongest shape you can make? And they'll go straight to the triangles for trusses and to tetrahedrids, because they distribute the energy so well. The strength and the stresses are all distributed evenly, and that's what's happening here. But in this case, the energy that's circulating through the electromagnetic fields of this matter topology are doing so in a way that gives strength to that structure. And that strength gives it a rigidity, gives it the substance that material particles have, as opposed to radiant mass energy, which we can't see or normally feel, but at the same time it can exert a force over distances. It's immaterial, so to speak. So we have a differentiation between immaterial mass energy, geometries, and material matter topologies, or physical matter topologies. But they're all derived from the geometry of an equilateral triangle, because they're all made from equilateral triangles of mass energy. Those triangles, again, just to highlight a side point, the geometry of them is such that when you add them together, or add additional ones to a field, you can expand that field as far as you want. It can either expand over time, or you can keep adding energy quanta to the field and make it bigger and bigger and bigger. Again, we're talking energy here. To simplify it, we're not talking mass or matter, but the arrangement of energy within that field must be always such that you end up with an equilateral geometry, h nu squared or mv squared. But the interesting thing that comes to light when you think about it is that number, the number of quanta that can be in that field, can be as large as you want. And this is probably the only time you'll see me mention infinity in Tetryonics, because you can keep adding and adding and adding energy, so long as you have an energy source, to that energy field, and it will geometrically get larger and larger to any number you care to pick. In the case of a field that has a linear momentum of infinity, as illustrated here, you would have infinity squared quanta making it up. And those quanta would again be the sum of odd numbers, or sequential odd numbers, from 1 to n, or n minus 1 to be precise, or infinity minus 1. So you add the numbers from 1 to infinity minus 1 and you'll sum up to infinity squared. These are all sort of things that Gauss played with when he was young. He never indicated any preference towards equilateral geometries, etc. But the relationships are hard to miss once you know a bit of his work and how he was summing things up. It keeps popping out, as does Euler's work keeps popping out and being explained. And we also have a normal distribution or a bell curve, albeit equilateral, arising from these numbers and their addition. That is to say, if we were to go to an infinity squared scalar energy field containing infinity squared number of Planck quanta, they would form a distribution going from one Planck quanta here up to a maximum amplitude of n, or infinity, and back down to 1. So the distribution pattern here would mirror what's going on. It's the square root, but it's a distribution pattern, albeit equilateral, that is mirrored in most mathematical books as a bell curve. Think of it as a triangulated bell curve. But in both cases, you have a normal distribution across the bottom, i.e. what creates an interference pattern. You have odd numbers, or the difference between squares, summing to form squared numbers, all within the equilateral geometry. So the geometrics are quite clear, and they're determined at an early stage by what can and cannot be done with a simple equilateral triangle. The properties of the equilateral triangle don't vary. They're very simple. The sides are all the same length. The angles are the same. The equilateral triangle probably has the distinction in Euclid's work, where despite some 13 books printed on geometric identities and proofs, the equilateral triangle probably gets mentioned, I think, about 4 times. It's basically, they say it has 3 equal sides, 3 equal angles. The height is the square root of 3 on 2, and they leave it at that. Which means that since that time, the equilateral triangle has been more or less ignored, despite the fact that now we can see that that simple geometry is the one that nature uses for everything. It's the one that brought about us and our speculation into the nature of nature itself. That geometry is the key, particularly when you equate it to quantized angular momentum, mass-OMEGA, which gives us Planck's constant, or the quantization of energy. Of course, energy, mass, velocity squared, when the energy content's varied, it creates a force, because the acceleration created on any object is proportional to the force that's applied to it, and that changes the velocity over time. So all these relationships, force, mass, energy, inertia, matter, things that we've been pondering over for centuries, if not millennia, can all be represented using the simplest of triangles, or simplest of geometric identities that's been overlooked for such a long time. How simple is this geometric identity? Well, for example, it can actually give us an answer to something that many electrical engineers and many physicists have been chasing for a long time. If we're describing electromagnetic energy, and that equilateral scalar energies themselves are the source of these electromagnetic fields, then we must be able to define something called the 0-point field, or in particular 0-point energy. Planck first introduced this term because when he quantized energy, he said he broke it up into small oscillators, quantum oscillators of electromagnetic energy. Einstein came along and called his photons quanta of electromagnetic energy, and the confusion began because Planck's formulation was h nu, E equals h nu, whereas Einstein's formulation using photons was E equals hf. Both are termed a measurement of the frequency. Hf is more appropriate for a frequency because it starts at a particular start point in the sine wave and finishes at the beginning of that same start point. If this was a positive charge, starting here and finishing here would not be the start of this point again, unless it was a series of these triangles. You would need to go from a positive to 0 through negative back to 0 in order to start again. That's what we see in a photon, a dual boson. Two bosons, two charges, a rhombic geometry. In the case of the Planck quanta, or the quantum in this case, we have a 0-point field, as I term it, a ZPF. It still has mass velocity squared, or Planck quanta, mass omega, nu squared. 1 by 1 is still 1. It has a square root linear momentum in accord with its geometric form, and it has electric and magnetic fields of equal field strength, but obviously one's electric and there are two magnetics. The h nu, which is a single charge either side of a quantum coin, must have a point where the electric field and the magnetic field originate or are seen, either originate from or are seen to originate from. And likewise with photons and any other field of energy. We now know that any scalar field of energy is equilateral, and it can be made up of bosons and or photons, depending on how you measure it. But in looking for or moving down this boson, which again is the smallest quantum of energy possible, we see that the electric field starts here, and as either we move or the particle moves, we see that the electric field builds up in strength or amplitude to this point and then begins decreasing. But as it decreases, the magnetic field builds up till we get to this point where there is no electric, but there is a magnetic dipole. So the electric and magnetic fields are said to be out of phase with each other. They're 90 degrees, or sine versus cosine relationships. Sorry, 180 degrees. No, 90. Measurement, that's a longitudinal measurement in line with the linear momentum. Measuring transversely at right angles to the motion of the particle or the observer, we see that the magnetic field, either the north or south, depending on what charge, starts at 0, increases to maximum, and then decreases to a minimum, just before it starts to increase again, but this time it would be of the opposite polarity. So if this was a north, it would decrease to 0 and begin to reappear as a south, or if it was a south, it would disappear and begin to reappear as a north, reaching its maximum and then diminishing again. But right at this point here, where the 0 is, there would be a minimum of electric and magnetic field force intensities. So if you were to measure the vector forces of the electric and or magnetic from any point around that particular 0 point, it would appear that the fields originate from there. That would be their source. That is what the 0 point is, or the singularity. That is where the electric and magnetic fields all converge to, and even later on, as we'll discuss, gravitational fields all converge to nothing. There is no black hole, there is no wormhole, there's nothing exotic there. It is simply the geometric convergent point, or convergence point, of the electric and magnetic fields. If you were examining a magnet, for example, and ignoring the electric field because it was neutralized, in a bar magnet you would call this the block wall, where the electric fields go to 0 and then come back out in the reverse polarity. Because it's a bar magnet, you wouldn't notice the electric field, but they are still present. This block wall, which is the 0-point singularity focus of the divergent electric and magnetic fields of the Planck quantum of mass-energy momenta, is what everyone's been chasing. 0-point energy. No energy comes out of that. 0-point energy itself, or 0-point field, is in fact the Planck quantum. It's this equilateral geometry, mass omega, Planck's constant. It's been known for a century now. But because we've focused on the mathematics rather than the geometry, we've completely overlooked or misunderstood what it is that is going on. Now that we have this geometry, we can begin to apply it and understand things much more clearly. We can understand where the positive and negative charges come from in the universe. They're opposite sides of this quantum coin. We can understand why electric fields, why energy contains an electric field and magnetic dipole in equal amounts, why there's no magnetic monopoles, because it always comes as a dipole, because the geometry of energy dictates that it must have this shape, must have this number, a squared number of quanta, and that it must be equally divided between the electric and magnetic components, as dictated by the omega geometry, the quantized angular momentum. And that this charge arrangement of north and south versus south and north on each side of a quantum coin can in fact be modeled as a short-circuited quantum inductive loop, where the electric energies circulate through an inductor at the base of the triangle to form either a north-south or a south-north magnetic bar magnet, and then continue back to recharge the battery only to circulate again. The reality is that flux, spin or curl does not exist. Only the equilateral geometry that you see is what exists. And our measurement of that geometry, either as it passes it into or beyond past the detector, or as the detector moves towards it, is what we interpret as the sinusoidal waveforms out of phase of electric and magnetic fields, of energy or mass energy as it propagates through any region, or as we measure it. The upshot of this is obviously that we've quite obviously been using the wrong geometry to describe energy. Special relativity and most physics, when it comes to energy, resorts to a right-angled triangle. All well and good, but it's the wrong geometry. The kinetic energy component, easily explained here in Tetryonics as half mv squared, or half mc squared in this case, not so easily drawn here. The right-angled triangle illustration implies that as you add more energy, the curve gets closer and closer to the point where to go past C, you would require infinite amount of energy, C squared, or more than that. Tetryonics shows us that that's not the case. To get to C squared, or a velocity of C, you require an incremental increase of odd number Planck quanta from 1 through to and including C minus 1, and then the addition of C plus 1 to it would take you past C. What's been missing are two things. One is the right geometry, obviously. The second is the understanding of what form of energy to apply to a particle, how to apply it, and secondly, that the geometry, not the mathematics, dictates what the limits are. A geometric graph of mc squared and the energies required implies a diminishing return. The same thing happens within the equilateral geometry. You require more and more energy for each and every energy level, n plus 1, 2n plus 1, 3n plus 1, etc. You keep going. When you reach just below C, you're still requiring a huge amount of energy, C squared quanta, but to go past C, you simply continue to add energy per second. It's a matter of releasing the right amount of energy, or the right number of quantity in the right form, within the right time frame. To date, all the acceleration technologies we have rely on a transverse oscillation rather than a Teslian longitudinal impulse. And that's the key to going faster than C, upsetting the textbooks and explaining many things, including older established experiments like Wheatstone and Tesla's own experiments. This mv h nu squared for energy has no limitation. It's not limited to the speed of light. What's limited to the speed of light is the transverse acceleration of material objects. Again, we'll go into this more detail, far more detail, in the QED section of Tetryonics. But suffice to say, at this stage, the speed of light is not a barrier. It's just a convenient yardstick with which we use to define our spatial coordinates in physics. Simple as that. The v squared per c squared is just a number of Planck quanta per spatial coordinate unit. We've touched on that many times before. So we can now define energy as a timeless measure of the Planck quanta, or the quantum chunks of energy that are available to exert a force or do work over a distance. And that's the basic definition of Planck's constant, the quantum of action to be able to exert a force over a set distance. The more you have, the more work you can do, the more force you can exert. That's the essence of energy. If you want to measure the mass or the impedance, the inertial mass of a field or a particle, you have to measure its energy content, and more specifically, the reluctance of that energy to change, to forces applied to it. Obviously, those familiar with electrical mechanics will know that if you take the energy off a short-circuited inductor that's established a magnetic field, when the energy is removed, the magnetic field will start to collapse, which adds energy back. It doesn't want to change. It resists changes. And that's the definition of inertial mass. The two are equivalent. Inductive charges, inertial mass. They're the same thing at the quantum level. We term it spin, curl, flux, charge, because up until now, prior to Tetryonics, there hasn't been a clear understanding of what those terms are describing, or what inertial versus gravitational mass are, because matter's not explained properly. We now know that matter's made up of inertial masses. And we can go on to explain the quantum source of gravity, the quantum source of inertial masses, which at the moment is explained as a Higgs boson. The bigger your Higgs particle, which isn't a particle at all, it's a field in Tetryonics, the more triangles you have in each charge fascia, which are made up of smaller inductive circuits, the more resistance there is to moving through a field of energy, which is what space is all about. It's full of radiant mass energies, irradiated light from stars, leftover Big Bang energy. As matter tries to move, or is pushed by a force to accelerate it, these fascia encounter those fields. And those inductive loops don't want to increase or decrease their energies, so they resist those changes. That's the essence of inertial mass in matter. That inductive resistance is the same as inertial mass. The one and the two words are the same. So we can begin to apply electrical engineering terms back to quantum physics and our understanding of mass and its role in matter, and how to differentiate mass from matter. What do all these things mean? All these explanations I've been saying and going on about? It means that for the first time ever in physics, we have the ability to unify physics at the quantum level and to explain it. In short, if mathematics is the language of science, equilateral geometry is its grammar. Up until now, mathematics has been a language in search of a grammar. It has no form. It is only a descriptive tool. It is like using our alphabet without the vowels. or hoping for the occasional vowel to pop in to make sense of a word. Or even worse still, it's like saying, as they did previously, in order to study the Bible, you had to learn Latin. If you didn't know Latin, you could never understand the Word of God. No different in quantum mechanics. Many times I hear, if you don't understand high-order algebra and relativistic mechanics, I'm afraid I won't be able to explain gravitation to you. Not on anymore. Tetryonics gives us a window where even if you don't want to understand the mathematics, you can certainly see, visualize, and manipulate the underlying geometries. It actually boils down to nothing more than a child's game of putting triangles together. You simply put the opposite colors up against each other and see what shapes you can make. The language is that simple. It's so simple it's used by nature, and it gives us the universe that we see now. So hopefully I've covered enough in this quick one on the geometrics to give you a good solid foundation and an explanation of how these things come together and the importance of geometry over pure math, and how and why nature uses that geometry. There are no supercomputers in nature. Nature simply is. It's the result of opposite charges coming together. And I'll touch more on that in the next lecture. Thanks for your attention and following this through to the end. If you've got any questions, please feel free to contact me directly via message, and I'll get back to you as soon as possible, and if necessary spend as much time as needed to explain any of these topics that I've brought up and discussed here. Thanks.